Dan Buffer, Chattanooga State, topic fundamental theorem of calculus. Okay, we're gonna go ahead and first start by reviewing a couple of things. So in other courses, we talked about the limits. So in trig, you guys did a lot of stuff with limits, understanding asymptotes, things like that. Earlier in this course, we used limits to find the instantaneous rate of change. So we talked about, if you've got a function like this right here, this 2x plus 5, the rate of change is changing. So how do we find the instantaneous rate of change? Well, what we did is we tried to keep on finding, we did the secant line becoming the tangent line, and we finally said what we can do is keep on, we can change our delta h, delta x, make it smaller and smaller and smaller, and essentially let h go to 0, and then do this kind of thing right here. And you can see even for a very basic function, this is a lot of work, and most people don't like it, it's not very fun, blah, 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 blah. And if I said to do this kind of thing for this function, you'd probably start crying. But then when we started to introduce the idea of the derivatives being the quicker version of that, it's very easy. The derivative of f of x is just f prime of x is 2. Boom. Over here, if I want to find the derivative of g of x, of g prime of x is 6x minus 4. Bam, easy, right? We all really, really liked that. So we did a lot of those examples, and then we said, well, what if we go the opposite way? What if we have some kind of some function and we want to find the antiderivative, the guy whose derivative is our function? So if we start with x squared plus 6x minus 4, our antiderivative is going to be, this isn't too difficult, it'll just be x cubed 3 plus 6x squared over 2 minus 4x. Then we do this plus c thing, because really, when we're finding the derivative, any constant goes to 0. So that could be plus 1,000, minus 2,000, doesn't matter. So we did a few of those and played with that, not very hard. Okay, then at the beginning of this chapter, we started with an integral, the idea of an integral, and we defined an integral as the area under the curve. So, and you probably thought this was kind of silly, like we're doing basic geometry, right? If this is our curve, this is our function, we want to find the area under the curve, so the integral of this guy, the integral from 0 to 6 of, we'll call this function f of t, doesn't really matter what we call it. Well, this is just a 1 by 2 rectangle, so that's 2. This is a 5 by 4 rectangle, that's 20. Okay, we're just adding up the rectangles, right? We get 22 for our area. So again, not very complicated, but not very helpful. Then we said, what if we have a goofy function? And let's go take a look at our Desmos calculator. Let's say our function is something fun like this. 16 cosine of x divided by x plus 6. Well, it looks like this. The function itself isn't too bad, but finding the area under the curve is going to be pretty difficult, right? The rectangles don't really do it justice. And what we showed is if with 2 rectangles, get a pretty bad approximation. And with, I don't know, 7 rectangles, we get a better approximation, but it's not perfect. But that starts to look pretty darn good. And as we get more and more rectangles, we get a better and better approximation. And if we can just take 69, 73 rectangles, we're going to get a pretty darn good approximation of what's the area underneath this curve. That's great news. The bad news is taking to 73 different rectangles is not so fun. We don't like that so much. When you do stats, by the way, you're going to come back to that quite a bit. So it would be great if there was a faster, better way to do that. Well, as luck would have it, there is. So here's our fundamental theorem of calculus. Let f of x be a continuous function on a and b, then capital A of x is equal to the integral from little a to x, f of t dt. This function is continuous on a and b, and it's differentiable on a, b. I'll explain the difference between these two in a little while. And his derivative is equal to f of x. Now, for most people, they see that and they just do, ugh. So we're gonna go ahead and break it down step by step and show you what you wanna be seeing when they say that. What they're saying is, if I have a graph like this, some function like this, right? So this is my f of t, this is my initial function, right? We're gonna define a new function, a of x, where if you tell me some number x in between a and b, it will give you the area under the curve, right? A of x is the function that gives you the area of f of t, the area under f of t, up to the point of x, right? Well, it turns out there's a relationship between this function and this function. Specifically, this guy is the antiderivative of this, and it's gonna kind of put all this stuff together. If you know nothing else, That's the thing I wanted to take away from this part one, that we are making a relationship between the integral, the area under the curve, and the antiderivative. There's a proof. I'm definitely going to show you the proof. I'm definitely not going to show you the proof right now. It's something that's going to be kind of weedy, a little hard to wrap your mind around. As you do more and more examples, it will make more sense. There are some examples in the book where they're going to want you to use this. They're going to say things like, if f of x is equal to, write this down, make sure we're talking about the integral from a to x of t squared cosine t dt, they're going to say find f prime of x. Okay, and you're going to go, what? Is this guy continuous? Well, it's continuous everywhere, so it's certainly continuous from some number here to some x. Okay, like let's say they gave you, by the way, let's just so you see numbers involved. Let's say it was from 6 to, I don't know, to 100 or whatever. This thing's continuous everywhere. It's definitely continuous over those things. That means the antiderivative is also continuous and it's differentiable. And finally, this thing right here, a prime of x equals f of x. In this situation, I know it's a little weird using the same letters over and over again. This a prime of x is this f prime of x. In this f of x, it's this function, but where x is the variable. So it's going to be x squared cosine of x. If you're anything like me, you found that explanation of that example most unsatisfying. And I get that. It's going to take a little while to kind of click and start coming together. The second part would be far, far more satisfying. So, and we can do one more example of this later if you want to see it. For the moment, let's erase it. Let's erase this. Let's go to part two. If f, some function is continuous on AB, then the integral, the area under the curve, of f of x dx is equal to its antiderivative evaluated at the points a and b and then subtracted. So the antiderivative evaluated at this point, evaluated at this point, subtracting the two. And where f is some antiderivative. Different books will define it slightly differently. It doesn't matter which antiderivative you get, so we're going to use the easy one in all the cases. Let's go ahead and do this, and you're going to find this, as I said, a lot more satisfying. Okay. What is the integral from 0 to 2 of x squared dx? So in picture form, this is what we're looking at. Here's the function x squared. This is 0. This is 2. This would be 4, obviously. And we want to find all of this area right here. So again, we could draw 73 rectangles, if you'd like, or we're going to go ahead and use our little theorem here. The antiderivative is quite easy. It's just x cubed over 3. And we're going to evaluate it at 0 and 3 and subtract the difference. You're going to also see it sometimes written like this. Different notation, same idea. It means you've already found that antiderivative. Now we're going to go and plug in the numbers. 3, oh, you know what? Let's not make mistakes as we do it. That'll definitely help us out. Evaluate it from 0 to 2. We plug the 2 in, 2 cubed is 8. 3, 0 cubed is 0. Our answer is 8/3. Once again, way easier than finding 1,000 rectangles. Let's do a slightly more difficult one. 2, yeah. 9 minus x squared dx. Again, first we check to make sure this guy is continuous. It is. Then we go ahead and find the antiderivative, 9x minus x cubed over 3. We're going to evaluate it from -1 to 2. So we're going to go ahead and plug the number 2 in for all of our x's. It gives us 18 minus 8/3. Right? Minus, and then now we're going to plug in the -1. It's going to be very important to make sure you keep your negative signs all good when you're doing this. -9 ends up being, I think, minus plus 1/3. 24. Double check me, make sure I'm not lying to you. I have no problems with that. If you have any questions about the theorems, we can answer them now so we can clarify a little bit, and then we're going to start doing some examples in groups. I'll come around and see how you're doing.